The next paper is constraint control schemes for the manipulation of heavy prefabricated elements with a lightweight robotic arm. And the presenter is Michele Ambrosino from Liberty Brussels University. So, yeah, floor is yours when ready.
Okay. All right, can you hear me?
Yes.
Okay, perfect. So, good morning, everyone. My name is Michele Ambrosino, and I'm a PhD student at the University of Brussels. My PhD is also in collaboration with the construction company Basics Group. So thank you for listening to this presentation. Today, I'm going to show you the results of our research that concern the developed, design, and the future implementation of a constraint control scheme for a robotic system to be able to place big and heavy prefabricated elements. So why robots for construction? So as many of my colleagues point out yesterday, basically, I think there are some lines not included. I'll show this. Okay, yeah. So we know that in manufacturing industry, robots change completely this kind of sector. Thanks to the use of robots, manufacturing industry is able to spread basically to increase profits, speed up the process, and lower basically the number of accidents. What happened in construction? So basically nothing changed. Mainly the only difference that you can see in this picture is that nowadays we care more about the safety of the masons thanks to the super fancy helmet that they have in this picture. So my project focused on construction activity, and in particular, the goal is to try to apply kind of robotization to this kind of activity. That is the bricklaying activity, one of the most famous and important activity in construction site. Currently, this activity is performed by a team of 2 masons. We have 1 mason that controls basically the crane in order to move the block to the final position. And then a second mason here on the stairs basically manually finishes the positioning. As you can clearly see, this activity is a kind of repetitive task with, of course, a high level of risk, especially for the mason on the stairs or sometimes on the scaffolding. That's why the solution that we propose is to robotize this kind of activity. Now, today I'm going to show you only part of the robotic system that we propose in our project. Basically, the idea is to use the same crane that is currently used on the construction site in order to sustain almost all the weight of the block, and then use a small robot, a robotic manipulator, a robotic arm, in order to place the block with a high level of precision. It's something missed here in this presentation, and the fact that the robot actually, the mechanical design comprehends also a mobile base. So the robot is on mobile base in order to be able to move the robot around the construction site. So the challenge here is that we have to design a control scheme to be able to control in a correct way these 2 machines. So we have the crane and we have the robot. So that's why at the beginning I say a robotic system. So which are the goals? The first goal of our control scheme is to ensure safe cooperation. Why safe? Because basically this kind of big elements, this kind of big blocks, knowing us and line blocks, can weigh over 100 kilograms. Of course, the robot itself alone cannot handle a payload of 100 kilograms. This specific robot, that is an EWA 14, can manage a payload up to 14 kilograms. So the cooperation should be safe because, of course, during the operation, you must avoid that the robot is overloaded by the weight of the block itself. Then the cooperation, of course, must be correct in the sense that you want to place the block in this final position. So that's why we propose a control scheme that, of course, in the engineering point of view, has to start from a mathematical model. Then we can develop our control scheme. And then, of course, we can make some simulation in order to prove the feasibility and the efficiency of our approach. In the next few slides, I will explain you how we obtain the mathematical model and how you can design the control scheme. One small details, the equation that you will see are quite ugly, So please don't focus too much on the mathematical expression, but I will try to explain you actually the physical meaning. So let's start from the mathematical model. First, we have the robot. So as typically, we can define the configuration of the robot thanks to its joint coordinates. In this case, 7 variables because it's a 7 degrees of freedom of robot. Then we have our hoisting mechanism. In this presentation, I'm focused only on the hoisting mechanism. So basically the possibility to move the crane only on one axis, on the X-plane, and go up and down, so to change the variable, the length of the cable. Then what you have to do is to put the two systems together. In a mechanical point of view, this means that we have to impose some constraints. What we have to do? So basically, we can consider the so-called direct kinematics of the robot that basically allow us to obtain this final position of the robot as a function of the robot joint coordinates. Then the same point actually can be expressed also as a function of the, let's say, pendulum coordinate. And what we have to impose, of course, is that in this position, this point, the difference between these two equations must be equal to 0. These are the constraints that we have to take into account in our when we have to develop the mathematical model of the system. Then, by following the super famous Eulero-Lagrange approach, what you can obtain is a dynamic model like that, in which basically you have the inertia matrix of the entire system, the Coriolis matrix, the gravitational vector, the control input, and then you have the Jacobian of the entire system, the force that comes from the environment. And this force actually came from the constraints. What we can do, but I want to go into details of that, you can rewrite in this model in this second form. Why? Because this second form allows you to design in easy way the control scheme. At the beginning of the presentation, I told you that the goal is to develop a constraint control scheme. So why constraint control? Because of course, when you want to control a mechanical model like that, you have to take into account that you have some constraints on position, some constraints of velocity. Basically, when you open the data sheet of the robot, you know that you cannot move the robot in all the configuration that you want because you have mechanical limits. And for the same reason, you have a limitation in velocity. But most important things in this application are the torque limits. These are for the robot, in purple are for the hoisting mechanism. Why torque constraints? So why we have to consider also the torque limits? Because as I told you before, we have to ensure that during the positioning, the robot is not overloaded. So actually we know that the actuators of the robot cannot provide more than a certain torque. So we decide in our project to develop a constraint control scheme that belongs to the so-called theory of the explicit reference governor. So basically, why this and not the famous, for instance, MPC? Because this system is really huge. So we have only for the robot 14 states. If we add the other 14 states of the hoisting mechanism, we come out with a model of 28 states. And also because MPC solve real-time optimization problem. So if you want later implement, cannot be so easy. Instead, the theory of the explicit reference governor confirm basically an internal loop that has to stabilize the entire system. And then you have to develop an add-on unit that modify your desired reference to an applied reference in order to be able that this applied reference does not violate the constraints. The main benefit is that this unit does not rely on any online optimization problem. So you can easily implement for a robotic system. So let's speak now about the control part. First, we have to pre-stabilize the system. What we propose is to pre-stabilize it with a PD plus gravity compensation that is well known in the robotic community. Then you have to prove that this PD, in this case, my HPD, is able to pre-stabilize the system. And you can do this with the stability analysis by Lyapunov approach. And then we can focus on this add-on unit. How this add-on unit works? Basically, you have to define two main functions. You have this function, rho, and the second function, delta. Rho, that is a so-called navigation field, is basically the distance between where am I and where I want to go. In this paper, I want to go really into the details, but basically this function can be obtained as a sum of two functions, an attraction term that basically point through the desired reference, and a repulsion term that basically point away from the constraints. So this is a vector, and basically is the classical trajectory planning. Then you have basically the dynamic safety margin. The dynamic safety margin is basically a safety margin, actually, that allow me to change the rate, basically the rate of the applied reference could be in such a way constraints are not violated. There are several ways in which you can basically define the dynamic safety margin. One that we propose in our paper is the so-called trajectory planning. Basically, you have to consider the dynamic model of your system, the pre-stabilized controller, your Lyapunov function. You make some simulation, and what you come out are several basically thresholds in which basically you compute the distance between the predicted trajectory and your constraints. And so you can take the minimum of this fourth function. Why the minimum? Because we are using a conservative approach. And why the maximum between the minimum and 0? Because of course, if all the constraints are violated, here you have -1. And so -1, it means that the next step, you can violate the constraint. So it's better if you don't change the applied reference at the next step. So now I'm going to show you some simulation that we perform on our CAD simulator environment. That is a realistic physical simulator environment in which, as you can see here, the block that we use in this simulation weight more than the maximum payload of the robot, because here we have a block of 120 kilograms. So in this basically video, you can see how the robot is able to move in cooperation with the hoisting mechanism, the block before on one axis and then go down. What we can see from the results is basically the fact that the position are always without the limits. So constraints are satisfied for the position. For the torque, the robot is never overloaded, and the same for the velocity, so we are always within the limit. Before to conclude my presentation, I'd like to show you some of the next step of this project. Basically, we are working on a full-scale demonstrator. Here we have a Kuga UA14, and as you can see here, we have an overhead crane that allow us to go in this direction and this direction. And we had performed some experiments, some first experiment several weeks ago, in which we are able to move actually the block to its final position in this case. Why this is just a first step? Because in this case, the block weighs 14 kilograms. Instead, our goal is to reach the 100 kilograms or more. So in conclusion, today I show in my research how you can develop and later on implement a constraint control scheme for a robotic system in order to place correctly big and heavy prefabricated elements. Why prefabricated elements and not block? Because the same approach can be easily extended to any kind of heavy prefabricated elements. Before to conclude, I'd also like to tell you that we have a YouTube channel in which we upload all our results each week, basically. So with this, I conclude my presentation. And if you have any question, it will be my pleasure to answer them.
Okay, thank you very much, Michael, for your presentation. So we over time a little bit. So yeah, let's move on to the next one. If we have any question, maybe we have time. Maybe someone can ask in the end. So yeah. Okay. Right. Let's.